right, so we've gone through a couple of examples of analysis already. And before we proceed, I just wanted to make sure that we remembered those examples. One of them, of course, was the linked list, right? That linked list, the bad linked list, the bad usage of, right? We came up with, the way that we did that is we created a table to quantify the number of operations, right? And then sum them up. And remember, the tool that we used to do that was Gauss's formula, right? And we proved that. Yeah, I think we proved it using induction yesterday. But in any case, that's going to come up a lot, because anytime you have a loop within a loop, right, you're probably going to bring Gauss's formula to solve that. Then we also looked at linear search, right? Linear search was pretty straightforward, but we did consider the best, worst, or average case, right? And then we decided we looked only at the worst case, right? And that was pretty straightforward because it was just a simple for loop, and you know how many times that for loop executes with respect to n. Then we did binary search, and we did this fully, I believe, right? Log n or something like that. We did the analysis, I mean. Here we also created a table, but we had to use math to reason about how many iterations or rows in the table there were, right? And we came up with a logarithm, like log plus 1, log n plus 1, right? Let's look at an older one that we've looked at before called selection sort, right? Now remember that selection sort works by going through and finding the minimum and then placing that at the front. Goes through and finds the second minimum, places that as the second. Goes through and finds the third minimum and places it at the third location. We're not going to write the pseudocode because you can look that up in any textbook. Instead, I'm going to give you the pseudocode, and we are going to analyze it. Right? The input is a collection, and we're using one indexing here because it starts at 1, goes up to n. And then we're going to output a sorted collection in non-decreasing order, right? Or we're going to manipulate the collection and swap it, right? We are starting our outer for loop here from 1 up to n minus 1, right? We stop short because if you've sorted if there are 10 of them, and I've sorted the first 9 of them, then where's that 10th guy? Right where he needs to be, right? So we stop short here of looking at the last one. Otherwise, we assume that the ith one is the minimum, and then go through all of the others, I plus 1, I plus 2, I plus 3, all the way up to and including n. And if we ever find something that is less, we update our minimum. After we've found the minimum, we swap a sub I and the minimum. Right? So step 1, the input is a. That's clear. 2, the size is n. That's also clear because of good pseudocode. 3, what is my elementary operation? Now, we're not going to consider anything necessary for the control structure of the algorithm. There is an assignment, a comparison, and an addition, I++, every time you do this loop, every time you do this loop. But those are necessary for the control structure of the algorithm. We are doing an assignment here, and we're doing an assignment here, right? But you're doing things to get to that assignment. We are also doing a swap here, right? So which one do you want to look at? Do you want to look at a swap, or do you want to look at the comparison on line 4, right, to see if that's the minimum? Both of those would be completely valid. If you're coming from a perspective of we need to optimize this for a minimum number of swaps, memory reads or writes, then of course, yeah, go with that, because you need to know how many memory reads and writes there are, right? Although this is probably a memory read also, somehow, right? But if you're actually changing the contents of the array, then or the collection or whatever, then you'd want to focus over here. You would come up with a different analysis. You'd probably come up with that this is linear with respect to the number of swaps. Right? Instead, let's go ahead and go traditional here, and let's go ahead and consider that comparison right there. So this is why you number your lines, because it's going to be the comparison on line 4, right? And then because you don't have a highlighter like I do, right? Okay. Now, how are we going to analyze this? I'm going to work from the inside out. I'm going to focus on, first of all, where we do the comparison, right? Pretend like there's no other code at all, just this one that I've highlighted. There's no other code. How many comparisons do you see? Not a trick question, just one, right? All right, now let's take and focus outward. Right? We're going to expand our consideration to this code block. How many times is that inner code block executed with respect to this for loop? Right? Now you might immediately see how many by just thinking, oh, well, it goes from I+1 to n, so that must be something, no spoilers though, right? Let's go ahead and set up a summation though, right? J running from I+1 up to n, right? You're going 1 plus 1 plus 1 plus 1 that many times, right? Now let's expand it out further and look at this code block, right? No, all of it. Can I edit it? No, I can't edit it, sorry. I can only undo it, and I'm not gonna undo it. So that is a summation from I running from 1 up to n minus 1, okay? So this involves creating a summation, and now we need to solve for it, right? Yes, you could plug this into Wolfram Alpha and find the summation really quick, but let's go ahead and practice our mathematical reasoning skills here. Let's solve the inner summation first. This is 1 plus 1 plus 1 plus 1. How many times? N times? N minus what? I, right? So you immediately jump to that this is going to be equal to, don't lose your outer summation, by the way, n minus 1 of n minus I right there. For those of you that do not understand how we got that, well, here's one way of reasoning it. If you were to go 1 plus 1 plus 1 plus dot 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 plus 1, starting at index I. So suppose that J ran from 1, 2, 3, dot, 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 up to I minus 1, then I, so another 1 here, plus dot, 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 plus n, right? Or sorry, plus 1, n right there, right? In total, how many do you have here? Well, 1, 2, 3, dot, 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 n. So in total, what you have is n ones, right? You don't have that. Instead, you start at I. I plus 1, I guess. Sorry, I plus 1. Right? So let's go ahead and get rid of that. There, right? That's my question mark right there. Right? How many did we skip? We skipped I of them. Right? So how many are left over here? N minus I, which is what you gave me. Right? Okay? All right, there's a nice visual reasoning for that. Summation of sums is equal to the sum of summations. So I running from n minus 1 of n minus summation of I running from 1 up to n minus 1 of I. Right? This is a summation here. It's just a negation. All right, what about this guy right here? That's n plus n plus n plus n. How many times? N minus 1 times. Because here you do start at 1. And you go all the way up to and include n minus 1. Right? N minus 1 n's is n times n minus 1. Minus. This is our old friend Gauss here. Right? Remember Gauss's formula. Might as well just commit it to memory at some point. It's going to be n times n plus 1 all over 2. Right? We don't have n up here. Instead, we go n minus 1. So we could take this and subtract off that n, right, and then figure it out algebraically. Or we could just take n minus 1 and plug it in for n up here. N minus 1 and n minus 1 plus 1. Those two cancel out, and you're left with n times n minus 1 all over 2. 2. Right? The second one is half the first, so it's n minus 1 all over 2. Okay? And that's it. Right? That's step 4 for selection sorts. Okay? So for selection sort, how did we go about that? Right? We set up a series, or it's not, I don't want to say series because it's not a series. Set up a couple of summations, solved them. Right? So it required some math, not advanced math, but solved them. and used Gauss's formula. And like I said, Gauss's formula is going to pop up all the time because you're doing a loop within a loop, right? If you do a loop within a loop within a loop, then you're going to have like n cubed, right? But then there is a closed form solution for that too. But any particular loop within a loop within a loop within a loop is going to have some closed form solution. You just have to look it up. Memorize Gauss's formula, but don't memorize the rest of them, right? Okay. All right. Another example, insertion sort. Right? Do we remember how insertion sort works? Let's pull it up. Insertion sort, right there. Right? Okay. What I'm going to do is I'm going to jump right into the middle of the algorithm. We've sorted values 2, 7, 8, 4, 9, and 12. And now we've got 3, right? So this is sorted. This is the sorted section. This is the rest of it, right? To be sorted. Right? And then we're looking at a sub I right here. This is a sub I, right? Okay. What we're going to do is we're going to determine where it belongs over here so that we can insert it where it needs to be. The way that we do that is by saving it off into a temporary variable over here. X is going to take on the value 3. Then we go into this while loop. We establish J right here. J pointing right there. Okay? And then we're going to compare the one right before it to X. Right? This one here is just to make sure that as we decrement J and J moves over here, because we're going to decrement it, that it doesn't fall off the edge of the array. Right? That if we get over here to J, that's when we stop. Okay? And we check. If the thing that we're looking at is the one previous to it is less than X, right? Then that means that we shift it over. And so I'm going to shift over 12. Okay, fine. 12. Okay. I update my J here. Get my J to this one. So that now I'm looking at 9. 9 versus 3. 9 needs to be shifted over. There we go. Now you see why we put it over into a temporary variable over here. Otherwise, we would have overwritten it and lost it. Right? 8 is going to have to be shifted over. 8. 7 is going to have to be shifted over. I didn't want to get rid of that. And at that point, we're looking at 2. 2 is not greater than 3. And so we stop with this while loop. Then what do? We take X and place it right there. Right? So this ends up becoming 3. Sorry. We don't do that. 2 is right there. This ends up becoming 3. Right there. We inserted it where it needs to be. Now for this one, how many comparisons did I end up having to make? I made a comparison of X to 1, 2, 3, 4, 5 elements. Right? What iteration was that, by the way? This is 1, 2, 3, 4, 5, 6. Right? So in this case, I made 5, generally, I minus 1 comparisons. All right, let's clean this up. And it's 2, 3, 7, 8, 9, 12. 2, 3, 7, 8, 9, 12. I think it was. Now let's suppose that the next one is 50. Am I going to have to shift everything over? Immediately what happens here? I find out that it's where it needs to be. So even though I saved it off over here in X, it ends up coming right back to where it started. Right? How many comparisons did I make there? Just 1. Right? So my reasoning is going to have to be very similar to linear search. We're going to have to consider a best case, worst case, average case if you want to. Right? So here's my first observation. The outer for loop, it runs I from 2 up to n. In other words, what's the total number of times it runs? N minus 1 times. Right? That's invariant. Right? It doesn't change. It doesn't change based on the contents of the original, and it doesn't change based on the size. I mean, it changes based on the size, but nothing else. Okay. What about this while loop? And by the way, this is my comparison right here. Right. I'm not considering that comparison because it is necessary for the control structure of the algorithm. Right. So I'm considering that one right there. How many times does this execute before I am able to jump out of this while loop here? Let's consider a couple of cases. The inner while loop. Right. What about the best case? Best case is going to be one comparison. And by the way, if you did that for every single iteration, what would it look like? 2 is where it needs to be. 3, just make one comparison there. See where it needs to be. 7, make one comparison. It's where it needs to be, right? In other words, it's already sorted, and you end up everything. I don't need to insert anything because it's all everything is where it needs to be, right? So in total, because the outer for loop executes n minus 1 times, and we only do one comparison each time, then the total is going to be n minus 1. Ooh, it's a linear sorting algorithm, right? It's a linear verification algorithm, right? Let's consider the worst case. Right? On iteration I, we make how many comparisons? Right? So suppose this is my I right here. In other words, 1, 2, 3, 4, 5, 6. Right? And this is not 50 anymore. This is 1. Right? So this is 1, 2, 3, 4, 5, 6, 7. In other words, I is equal to 7. The worst case is I'm going to have to make a comparison there. 1, 2, 3, 4, 5, 6. If that pattern holds, how many comparisons do I end up making? I minus 1 comparisons. Right? So what's the total here? It's going to be another summation. I running from 2 up to n minus 1. That's the outer for loop there. And then you're making I minus 1 comparisons on each iteration. Right? Duplicate that and come over here to solve it. Summation of sums is equal to the sum of summations. So I starting at 2 up to n minus 1. N minus 1? Oh, sorry. I should have run, okay, so it's n minus 1 times, but I should have changed this to what? It goes up to n because it's 2 to n. There we go. Sorry about that. It looked wrong almost immediately. I should have caught that. All right, so that's n and that's n. Okay? I minus summation of I running from 2 up to n of 1. Right? And again, it's just the sum of summations equal to sum. Summation of sums is equal to the sum of summations. Right? Okay. What about that first one? What does that look like now? Gauss. But we don't start at 1. We start at 2. So it's going to be Gauss corrected by 1 because we never counted 1. We went 2 plus 3 plus 4 plus 5. What about this one? 1 plus 1 plus 1, how many times? N minus 1 times, so it's n minus 1. Right. What happens to that minus 1 minus minus 1? Cancels. N times n plus 1 all over 2 minus n. If you want to get that into a little nicer form, you can go 2 over 2, right? And that's going to be n squared plus n minus 2n all over 2, which is equal to n squared. The n cancels with the minus, one of the minuses, and so n all over 2. Right? Or n times n minus 1 all over 2. Hopefully that's starting to look really familiar. Right? That's exactly what we got for selection sort. Right? Right? I think so. Anyway, it's very, very similar to linked list. Right? It's going to be, ultimately, it's going to be n squared. So again, for insertion sort, we considered the best and worst case. and reasoned about the inner while loop, right? Then created a summation and solved it. Again with Gauss. Gauss was necessary there, right? We could keep looking at these. Like bubble sort would be just a straight up n squared, right? We could look at 5 different sorting algorithms and analyze them all. It gets kind of tedious, right? Unfortunately, a lot of computer science courses that I see, they just make up algorithms. Right? Here's a loop within a loop within a loop. Right? Come up with it just as an exercise. Right? It's all artificial. I don't like looking at artificial examples at all. I like looking at actual examples. So instead, what we'll go do is move on to the 5th step here, the fun stuff, asymptotics. Right? This is big O analysis. Step 5 is once you've got that function from step 4, is you provide an asymptotic characterization of its complexity. Right? The motivation is that we want to characterize an algorithm's performance with respect to the input size n. Right? And we're interested in how it grows as n tends towards infinity. Right? Because we're not concerned about small input sizes, 5, 10, 20, who cares? Everything is going to be immediate, right? Like in our demo. We started this out with this demo here, and both the linked list and the array-based list, they were both very, very fast on 10, 100, 1,000. It's only when you got up to 1 million that it started to make a huge difference, right? So we're not we're not concerned with small input sizes. Everything performs well for small inputs because computers are fast, right? And human perception is terrible, right? I mean, it is going to be off by several orders of magnitude, but the difference between a nanosecond and 5 nanoseconds is nothing to us because we can't perceive it. So the tool that we're going to use is big O analysis because it gives us the growth rate of the algorithm, right? Or algorithm's performance, right? All right? And it allows us to ignore constants and lower order terms. We'll see that in a second here. We like to ignore constants because, again, if my computer performs one operation in 5 nanoseconds and yours does it in 1 nanosecond, yours is 5 times faster, right? But that doesn't mean that the algorithm is faster. It just means your machine is faster. We like to ignore lower order terms because we want to focus on the most important one. Right? And so here's the definition. Right? And you probably have seen the definition if you've done 235 already. But this is the algebraic definition. This is not the original definition, by the way. The original definition is in terms of calculus. But this is an equivalent definition. Let f and g be 2 functions. For our purposes, they define the complexity of 2 algorithms, a and b. We say that f of n is big O of g of n if there is a positive constant c and an integer n naught such that f of n is less than or equal to c g of n. In other words, g of n is bounding f of n for all n greater than or equal to that n naught. Right? Now to understand this, let me look at an actual example. F of n, we're going to graph it visually. 175 n squared plus n. Right? And g of n is going to be n cubed for n running from 0 up to, say, 100. And please plot these. Plot. So Wolfram Alpha, I'm asking it to plot these 2 functions. And there it is. Right? I can zoom in. There we go. Right? All right. From that appearance, which one is the better function? From that appearance alone, which one is the better function? Remember, x-axis, that's input size. Y-axis is a resource measure, right? So if this are time, then higher means it takes more time. Lower means it takes less time. So what's your impression here? N cubed is better because it takes less time. Right? But that's for small input sizes, up to 100. What if I zoomed out on this and went to 200 instead? Predict what's going to happen here. At some point, they're going to cross over. Right? After that point, they will never intersect again. Right? And if I zoom out even further, it becomes abundantly clear that we were wrong in our first impression. Right? That no, n cubed is way worse than n squared over here, right? Over here, there is a crossover point that gives us a misimpression for small input sizes. Big O analysis gets rid of that and says, no. look at it in the limit. Look at it as it grows and grows and grows. At some point, right, this is that at some point, n naught. At some point, there's my n naught right there. This function will always be greater than that function over there. Okay? So, some terminology here before we actually start proving this stuff. Now, we technically we shouldn't be writing that. So technically incorrect. You should, technically is the best kind of correct, right? You should write that f of n is in O of g of n. So in 235, which one do you use? Have you gotten to that yet? Are you using this or this? All right, this one is correct because the thing on the left-hand side is a function. The thing on the right-hand side is a class of functions, a set of functions. And so when we've got a set, we use inclusion. Right? It makes no sense. What does equals mean? You can't have two different dissimilar things, a function and a set of functions, be equal. Right? That doesn't make any sense. But nevertheless, this is so common that, yeah, okay, we'll allow it. Right? All right. So pedantic's out of the way. Big O characterizes the relative rate of growth functions as n tends towards infinity. Right? One is going to be greater than or equal to the other one. F of n, in this case, has a less than or equal growth rate to g of n. And from g of n's perspective, g of n's is at least as big as f of n. That's because of this less than or equal to here. Right? It could be equal. It might not be equal. Right? They could have the same rate of growth. Right? So the following are true. Let me go ahead and look at examples here. Examples. So I could say 3n plus, or 3n plus 5 is big O of n. Right? That is certainly true. Right? This is true. It's the tightest possible bound. Because I've got a linear function on the left, and on the right, that's all linear functions. All functions of the form a, b plus, or a, n plus b. Right? But it's also true to write the following. 3n plus 5 is big O of n squared. Right? That's also true. It's just a loose bound. Right? You can be as loose as you want. Right? You can go say that it's also cubic. Right? That's also true. Right? This is the most true, though. Right? Right? It's the best because you're providing the best possible lower bounds. Right? You could also go, well, it's also certainly bigger, like any exponential function is going to be bigger than linear. So saying that's true too. Right? That's like saying 5 is less than or equal to 1 billion. Right? It's true, but I mean, you're nowhere close to each other. Right? What is not true, however, is if you go too low. Right? 3n plus 1 is big O of log n? No, that is false. Right? It would also be wrong to mix any other polynomial there. N squared is not big O of n. Right? These are not true. Okay. Again, big O only provides a asymptotic upper bound on the rate of growth of a function. It's not necessarily a tight bound. If you want a lower bound, or if you want a tight bound, then you would probably do this in 235. Others say big theta. Right? That's a tight bound, or tight bound. Right? In other words, f of n has exactly the same rate of growth as g of n. Or a lower bound would be omega, big omega. This would be a lower bound. Right? And it's just the same definition, but in reverse. Instead of this less than or equal to, it becomes greater than or equal to. So that's why we're not going to look at them. We're just going to look at big O because that's enough. That's sufficient. How do you go about proving these two things? Or how do you go about proving a bound like this? Given two functions, f of n and g of n, how do you show that f of n is big O of g of n? Right? Well, the first step, write out your intuition. Right? So these two functions that we just had over here, let me write them out. F of n, f of n is 175 n squared plus n, and g of n is n cubed. Right? Asymptotically, what is your intuition? Which one of these is bigger? G of n, right? So we want to prove that f of n is g of n. or big O of g of n, sorry, of g of n. All right? That means applying the definition, or at least for our first proof technique here. There it is. There's the definition. We have to find a c, and we have to find an n naught that this inequality holds. Okay? So there are two techniques that I'm going to show you. All right? The first one is going to be finding that crossover point. Right? You find a crossover point. That is the largest value of n for which the two functions intersect. They have the same value. That means algebraically finding that guy right down there wherever they intersected. Let me restore this back down to 200. There it is. I need to find that point right there. Because what I can then do is I could say, well, after that point, going one further, then this function is greater than that function, and that's the last possible intersection point. That means I need to find all intersection points, right? So basically what you're doing with this is that you're fixing C and finding n naught, right? And finding the n naught, right? The largest or big point, or largest slash last point that the two functions intersect, right? So mathematically, what does that mean? Let me come over here. If I set f of n equal to g of n, that means that's where they intersect, okay? So 175 n squared plus n is equal to n cubed. Let me collect the terms. N cubed minus 175 n squared minus n is equal to 0. Say what? Oh, sorry, was it plus n? I had plus n over here, but I took it to the other side. I'm taking all this stuff over here. Minus 175 minus n. There. I did that so that hopefully you can see that this is now in a form that looks familiar. Right? Setting something equal to 0 and finding and solving for n, that's called what? Finding roots, right? What's one of those roots immediately? 0, right? And certainly if you looked at this and you looked, if you zoomed in on that that origin right there, you would see that the two functions intersect, right? Okay? Where else do they intersect? Well, let me take out that root. And we're left with what? N squared minus 175n minus 1 is equal to 0. How do you find the other two roots? No, how do you know that they are three roots? Because this is a cubic equation, right? If they've got a polynomial of degree k, then you have k roots. Some of them could be repeated, in which case they're roots of multiplicity, right? But they're not going to be repeated in this case, I don't think. Now that I've simplified it down to a quadratic equation, though, what tool can you use? Quadratic formula. N is equal to negative b, so 175 plus minus square root of b squared, so 175 squared, minus 4ac, so that's plus 4, all over 2a, and a in this case is whatever. Right? I'm not even going to do that math. Right? Wolfram alpha. Roots of n squared minus 175n minus 1. Right, there we go. There's one root and there's the other root. Right? One root is equal to this negative value here. Is that going to be the root that I care about? No. Remember, we only care about the first quadrant in algorithm analysis. Why? Because there's no such thing as a negatively sized input. So that root n being negative 0.007 or something like that, who cares? Right? That's not even in our domain. Okay? That other root, however, which has a value of 175 and some change, n is equal to 175.005 ... right? That's the one we want. Right? Now you do have to be careful here because just like we don't care about negative values, do we care about non-integral values? Nope, because there's no such thing as an array of size 3.5. Right? So if I go out here to 175 and change, and this right here, that's where the crossover point is. What is the next integer value? 175. Right? Oh, sorry, 176, yes. Right, there we go. Right? So at 176, the functions, it's not diverge, but what is it? Like they will never, let me rewrite it then. For all n greater than or equal to n naught, which is equal to 175, right? You could go 176, there we go, 176. The functions will never intersect, right? So all we need to do now is determine, well, f and g, what happens at 176? Which one is greater? I'm not even going to bother doing that because it's going to be 176 squared plus 176 here, 176 cubed. You'll come out with a value here that it is greater than this one right here. All right, this one is greater, or sorry, g of n is greater than f of n. So there's my n naught, and my c this entire time was just simply 1, right? Because I was finding, I set them strictly equal to each other. So what was implicit here? C was 1. Okay. That was easy because I manufactured this result. I made sure that there were no constants over here so that I could get a trivial root, and then you could tell me all about the quadratic equation again. If I gave you a polynomial of degree 50, are you going to want to find all 50 roots? Right? Not even using a tool. Screw that. Right? Instead, what we're going to do is we're going to look at technique B. Right? Again, this is only easy if it's if the roots, finding the roots are easy. Technique B, right? We're going to simply set up an inequality, not an equality, but an inequality, and make make the function bigger and bigger until it matches g of n. Right? Okay. We're going to set up an inequality with f of n, I should say. And just make the function bigger and bigger. Not too big, just big enough, that Goldilocks zone. Right? Now, to understand what I mean by that, let's go all the way back to our little graphing here. Right? Yeah, we'll go ahead and keep it at 200. What if I made, say, this value here bigger? No. Let's make g of n bigger because that'll actually look a little bit better. So 3. Let's go ahead and make it bigger by twice. G of n. Right? Will you graph that? Are you smart enough to graph 3 things? It has to really think about it. No, it's not smart enough to do those. So are you smart enough to do it if I gave it in order? 2g of n. Or do I have to repeat myself? All right, I have to repeat myself then. All right, so 3n, or 2n cubed. There we go. At least I didn't have to give it a name, do I? I have to give it a name, fine. So g h. There we go. So I've simply made that function bigger. Remember that it was the blue was greater for everything up to 175. Let's zoom in on this. There we go. What I've done is I've taken that orange and I made it twice as big. Does multiplying by a scalar change the rate of growth of a function? No. It just changes its plot by moving it up here. I've taken this intersection point and I've moved it back over here now. Right, by doing that. Well, okay, it's still not at 0, so let's keep going. What if hi of n is equal to 3n cubed? There, I've moved it back even further. Whereas once it was over here at 175, now it's down over here less than 100. Now it's somewhere over here probably. Right? I don't know where it is. Right? But my goal here is to push it all the way back to 0. Right? So that my n naught is 0. That's essentially what I'm doing here, right? You are fixing n naught to be 0, possibly something bigger, right? N naught to be 0, and possibly changing it as you go along. And then you're finding that c sub n, right? This is my c sub n. First it was 1, then I made it 2, then I made it 3. I just made it bigger and bigger and bigger until I pushed that intersection point all the way back. Now, that's the description of it. The actual process is so much easier. Right? We start with f of n being 175n squared plus n. Right? We need to make it so that this is less than or equal to some c g of n. Right? For all n greater than or equal to 0. Right? So, how can I make this function bigger? Make it bigger and make it look like this function down here. Remember that g of n is, is n cubed. Right? So how can I make this function bigger? I could, I could multiply by n. That'd be going too far though. In fact, you can split this up. You can multiply that one by n, right? 175n squared, it'd be okay, but it'd be messy, right? Plus n squared, right? For all n greater than or equal to 0. That's true, right? All I'm doing is making this one term bigger. By making that one term bigger, I can collapse these into one term. This is equal now to 176n squared. It doesn't exactly look like this yet. It looks kind of like that, 176 here, but I have an n squared instead of n cubed. Well, guess what? 176n squared is less than or equal to n cubed for all n greater than or equal to 0. That is crucial. Is it true for negative values? Nope. This will always be positive for negative values. This will always be negative for negative values. Right? But as long as we're in the first quadrant, this is going to work. Right? So for C being 176 and n naught being 0, the inequality holds. Right? Isn't that so much easier? Right? All you have to do is make the function bigger and bigger and bigger. Don't make it too big, right? Because if I had multiplied by, I guess it would have worked. If I had multiplied by n, this would have been n cubed, and this would have been n squared, and then I could have made this into n cubed, and we would have gotten the same exact answer, right? As long as you are stating that it holds for all n greater than or equal to 0, holds for all n greater than or equal to 0, you certainly don't want to do that for logarithms because logarithms are not defined for 0, right? All right, you don't want to do it for things like where it's negative, right? Because then it's not true. That's technique B, right? You're setting up an inequality and making it bigger and bigger and bigger. This is much easier, right? Because all you have to do is make it big, right? In fact, there are an infinite number of combinations of C, comma, n naught that it will hold for. For example, I got my C here to be 176. It's also true for 200. It's also true for 201 and 203, right? Et cetera, et cetera. Right? So there are an infinite number of pairs. C is even easier if you know calculus, and I think we all know calculus here, right? You set up a limit, right? Some limits are obvious, some limits are not, right? So it requires some calculus because you need to understand how limits work. The numerator and denominator are growing, but the other one is not. That's obvious. And so yeah, we've got enough time. Let's do it really quick here for that. If I set up a limit here as n tends towards infinity of 175 n squared plus n all over n cubed, right? What's going to happen here? Well, first of all, the limit of sums is equal to the sum of limits. So as long as they converge, but whatever. Right? 175 n squared all over n cubed plus the limit as n tends towards infinity of n over n cubed. Right? Okay? Well, what happens in that first limit? Algebraically first, that cancels with that, and you're left with 175 over n. What happens to that? The top is not growing, the bottom is growing. So it converges to 0. what happens here? That cancels with that, and we're left with the limit as n tends towards infinity of 1 over n squared. 0. These are what I like to call obvious land, because you have a monotone increasing function on the bottom, a constant on the top. Of course, it's going to converge to 0. If you were in calculus class, could you just say that's equal to 0? I don't know, maybe you could. Would they accept that as a proof? All right. If you were in an analysis class, that would not be considered a proof. A proof would be that you have to come up with a epsilon, an epsilon, what is it? Epsilon, right? Epsilon x proof or something like that, where you basically have to prove the convergence. In other words, you'd be applying a definition that's basically this, right? But here, I think we're in obvious land, and we don't need calculus any further. Right? If it were the limit, all right, fine. Limit as n tends towards infinity of n over 1. Right? You're also in obvious land. That doesn't converge. What happens there? That diverges. Right? So we'll talk about the implications of convergence and divergence with respect to this technique on Monday. But of course, you can use calculus for this. All right? All right. In fact, we'll review some calculus and some examples here. Yay? All right. No? It's just the first derivative, no integrals.